Here's question 1 from the quiz. The flow is air, and some people missed that and used the wrong density. The basic idea is there's a flow coming this way, a block in its way that extends 10 meters in that direction and 1 meter this way. The CFD model for this 10 by 1 meter bluff body, this square block, in a cross flow, that flow there, predicts pressures on the front, this side, the side facing the flow, that are well approximated by this equation. And in this case, I just made up this equation. So it might not be the actual pressure, but it's the one you use in the question. So the pressure is highest where y is equal to 0, right here. And that actually is the stagnation point, because we expect, given this symmetry of this problem, that the flow will go the same way on both sides. And the streamline right down the middle will stop right there at a stagnation point. So yes, there's a stagnation point. It is right there. What will the pressure force be on the front of the surface resulting from the flow? Well, there's a high pressure here at the stagnation point, and according to this equation, it's tapering off somewhat towards the edges, but the pressure all over the front of this block is still higher than ambient pressure, i.e. it gives a positive gauge pressure. So what will the force be on the front? To get a force, we integrate a pressure over an area. And in this case, the area will go from the bottom up to the top and from the front to the back in the depth of the page. So the incremental area as we move over our domain of integration will be 10, the width, times dy. Now we've got symmetry, so we could do this integration just from 0 to 0.5 and multiply by 2. Or we can do it from negative 0.5 to 0.5 and we don't have to multiply by 2. Negative 0.5 to 0.5. This is p, 100 minus 20y squared. The depth into the page is 10 dy, and if we do that integration, we wind up with 983 newtons. A little further down, it asks, what is the velocity of the flow well upstream of the bluff body obstruction? Well, this is the stream. This is further upstream. So if we're well upstream, this flow distribution hasn't yet been disturbed by the bluff body. So we're looking at a pressure that's ambient and the flow moving at its regular free stream velocity. If we write Bernoulli between location 1 and location 2, then we'll see that we'll go from having 0 pressure and some velocity to having 0 velocity and some stagnation pressure. So from Bernoulli, with all the other terms crossed out, we're converting kinetic energy at location 1, the upstream location, into potential energy of pressure at the stagnation point. And it's a complete conversion. So if we take V1 squared over 2g equal to P2 over rho g, and we know that P2 is equal to P at y equals 0, which is just 100 pascals, then we can rearrange this equation this way, plug in the numbers that we've got, remembering to use 1.2 for the density, not 1,000, and get 12.9 meters per second.